Thank you guys for all your love and support. Till the last video we have completed the first module of our basic electronics subject. So let's do a quick revision of our first module. That the three chapters. That one is introduction to signal, second one is operational amplifier, and third one is semiconductor diode. So because a revision is much needed, only if you will read continuously chapter by chapter, it will not efficient. Once we will do a revision, it will remember what we have read before. So without wasting much time, let's start. First one is introduction to signal. So what is a signal? A signal is nothing but it is a time varying quantity which contains some information. From the signal we will get some information. That information is varied throughout the magnitude. If I will represent a signal in a sinusoidal wave, then throughout the magnitude of my signal, throughout the time, the information is contained. But what we are interested, we have to send that signal from one end to another end. For that, I have to transmit through some medium, or we have to do some process. So what is this? Is called signal processing. For that, our signal should be in current and voltage form, so that this current and voltage form signal can be transmitted over the electronics components. So how to represent a signal in current and voltage form, which is nothing but the Thevenin and Norton that we read. In Thevenin means voltage source with a series resistance and a load is connected. That is the Thevenin form. That is the signal represented in terms of voltage. So if a signal will represent in terms of current, then a current source with a parallel resistance, source resistance with a parallel load. That is called Norton case. So these are the two conditions that we read. If my load resistance should be very high than RS, then what will happen? In this voltage divider, the maximum voltage will occur here. If this resistance value is less, then it will obstruct less. So less voltage drop. Less voltage drop means whatever the voltage that I am supplying from here, that I will get that much voltage over here. Now in second case, that is in Norton case, my RS value should be very greater than RL. It means this resistance value should be very high. If this resistance is very high, means this resistance is very less. This resistance is very less means maximum current will flow through this, because current follow the less complicated path. So it will try to follow the second path, and maximum current means I will get maximum output at this side. Okay. So how to convert this any form of signal to current or voltage form? That is called transducer. So what is a transducer? A transducer convert one form of energy to another form. So let's take an example of microphone. When we are speaking in front of microphone, what it is doing? It is taking our sound wave, or that is called acoustic wave, and it is converting into electrical signal so that it can transmit for a long distance. And similarly, at the receiver end, we are using a loudspeaker. What the loudspeaker is doing? It is just converting the electrical signal into the acoustic wave, or that is sound wave, so that you can hear from that. Okay. Now, the frequency and time domain analysis. So what? A signal, any signal that can be represented either in time domain or frequency domain. See, this is a signal which is represented in terms of time. And there are certain signals that we have to represent in frequency. So how a signal can be represented in a frequency if a time domain signal is given? For that, we have to learn the frequency spectrum. That is the spectrum means it is the range of frequency. So for that we have to do Fourier series or Fourier transform. These are the two techniques, so that we can convert our signal from time to frequency. So what is Fourier series? Fourier series is applied only to period signal. If this is a signal which is having a period of t, because it is repeating again after this interval, so it has some certain period. But there are some other signals. Suppose this is a signal which have no periods. You see, the positive half and the negative half is not resemble with the positive half and negative half of the next cycle. It means it is not periodic signal. So for the period signal, we will do the Fourier series, and for the non-period signal, we will do the Fourier transform. Okay. Now if you remember that I did this I have taken this square wave and I derived the formula for in terms of voltage, in terms of frequency. How? This is a square wave which can be written in summation of some sine and cos component having different magnitude. If you remember, I wrote for this square wave, that is A0 plus A1 cos t plus A2 cos 2t, like that. Plus B1 sin t plus B2 sin 2t. And what we found, the A0, which is nothing but average value. Since this is a period signal which is having equal positive and negative half on both, then it has an average value which is nothing but 0. So what we got? Our A0 value is 0. And again for the cos component, that we are getting 0, because how to find the A0? A0 equal to 1 by t integration 0 to 2 f of t dt, that we are getting 0. how to find this a1, a2, a3, an? That is 1 by t integration, 2 by t integration 0 to 2 ft, again multiplying with cos component. And similarly for b1, b3, b3, if you will see the derivation, you will get what I am saying. So what at the end, what we got? We got our output voltage, which is nothing but sum of only, because a naught component 0 and a1 to an, that component also 0, and b component as 0 for which? For even term, and only for the odd term I am getting the output. This is the b1, this is b3, this is b5. Okay, so from this equation, from this output, I can draw my that signal in terms of frequency or omega. Omega is nothing but 2 pi f, so that is written in terms of f. So these are the components having the magnitude. So if I multiply 4b by pi with this, it will become 4b by pi into 1. Again 1 by 3 times 4b by pi. These are the magnitudes which is decreasing. You see the magnitudes are decreasing throughout the, if I am moving in the frequency axis. So my maximum energy is staying at the first 2 to 3 part. So, and this is the frequency domain analysis of any signal. Okay. The derivation already I've done this derivation on the video. You can follow that. Now, the elementary signal. There are three types of elementary signal. One is step, one is ramp, and one is impulse. So step is nothing but there is a change at some interval. Some signal having some amplitude, some different, and at certain interval it is changing. So you see ut, which is equal to a. This value is a for t greater than 0. As we are moving for the positive half of the positive side of this t, that is 0 for greater than 0. This is the fixed value of a, and for the negative, a value is this magnitude having 0. Okay, so you see here it looks like a step. That's why the name step. This is a step signal. What is unit step? If I'll take a value as 1, then it will become unit step. Unit step means a signal having a value 0 for t less than 0 and having a value 1 for t greater than 1. And t equal to 0, the signal we can take an average, or we can take a value which nothing but a, or this 1. Okay. Now this is ramp function. Ramp function is nothing but it is varies along with the time. Means if time is equal to 1, then my amplitude will be 1. Time equal to 2, amplitude will be 2. It means as t greater than equal 0, RT will be t. Whatever the value of t, RT will be same. And for t less than 0, the signal is 0. Okay. Then what we saw? We saw that our derivative of ramp is nothing but step. If you derive take the derivative of this ramp, it is straight line. So straight line means it will give me a constant value. This straight line, derivation of this straight line will give me a constant value. And if I will again do the derivation of the differentiation of this one, what I will get? I will get an impulse function. So impulse function is nothing but it has some amplitude of infinite, and the area under this impulse function is nothing but 1. Okay, area under the impulse. You see, if I will do minus infinite to infinite del t, which is nothing but impulse function, that will give me a unit step. Means it will give me a value 1. So area under this curve with any limit, that will give me a value 1. And if I will derive this step, I will get impulse. And if I will derive this ramp, I will get a step. Okay. So now this impulse function can be written in terms of a impulse train. That is, there are some shifting property that we read also. For this unit step, this is u of t minus t naught. T minus t naught means I have to move my step signal t naught unit towards right. If it will become t plus t naught, then I have to move my signal towards left by t naught unit. Similarly, as this is also a impulse function, so this impulse function can be written using this property del of t minus t naught, del of t plus t naught. Means this signal t minus t naught means it will occur here with a value t naught. T plus t naught means it will occur here with a value that is t naught value. Okay. So if I will add all those components from del of t naught, t 2 t naught, 3 t naught, and minus t naught, minus 2 t naught, so I will get a train of impulse. Okay, the train of impulse will help me to convert my analog signal to digital signal. We will see that one also. Now, analog and digital signal. What is analog signal? Analog signal, these are the continuous in time and continuous in amplitude. What does it mean? You see, this is an analog signal which is continuous in time axis and also continuous in magnitude axis. Okay, so this is the analog signal. So you see, these are some example of analog signal. These are the electrical signal, human speech, whatever we are speaking, that is in terms of analog signal, it is continuous in time, and I am not strucking anywhere. It means I am continuous in amplitude also. Okay. Now, what is a digital signal? Digital signal, it is being used to represent data as a sequence of discrete values. Okay. How to convert this digital signal from analog signal? Our analog signal, it is there. we have to, this is continuous in time and continuous in amplitude also. First we have to discretize this signal. It means discretize means discreting in terms of time. So my next signal, that is the discrete signal, it will become discrete in time but continuous in amplitude. That is discrete signal. Again, if I will convert that discrete in time and continuous amplitude into discrete in time and discrete in amplitude, then I will get my digital signal. It means my digital signal are discretized in terms of time also and in terms of amplitude also. So how this process can be done? This can be done there are certain processes like sampling, encoding. Using this process, I can convert my analog signal to digital signal. Okay. For the digital signal, the signals are the ranges which varies from 0 to 1. It means it has only two levels, 0 or 1. But in analog signal, there are different level of magnitude. Okay. Then to represent this digital signal, which number system is best? To represent this digital signal, our binary number system is very easy and best method. We will in our third module after this video we will start that number series also. So we will see how best binary number is easy. So to represent the digital signal, binary number system is the easiest method. Now suppose I have a n binary digit to represent the sample of analog signal, then the discrete signal will be, so I have some number of bits. This is the number of bits, n equal number of binary signal bits, that is nothing but B0, B1, B2, B3 like this. If I have this B1, B2, B3, then I can represent my digitized sample signal. This signal I can get like this B0 2 power 0 like this. Suppose let's take an example of, suppose the B0 value that I did in a video series, that is 1001. So 1001 means in place of, if I am writing 1, if I am writing 1001, it means it is the my LSB, lower significant value, that is nothing but B0. This is my MSB, most significant value. So if I multiply like this is nothing but B0 into 2 power 0 into 2 power 1 into 2 power 2 into 2 power 3. So this is nothing but 8, this is nothing but 1. So this 2 are 0, so it is 8 plus 1 which will give me 9. So 1001 means it is a value 9. Okay. As this number of these bits, as these bits will increase, then what does it mean? It means I am getting a perfect signal. Whatever I am sending from my transmitter side, I am getting that same signal at my receiver side. If the number of bits is increased, it means for every fraction, if you see this analog signal, if you will see this analog signal, if I will discretize at each and every fraction of amplitude, I am increasing my number of n. It means at my output side I will get the exact signal. So if my n value will increase, then what will happen? Then error will be less. Error less means whatever I am sending at the transmitter side, the same signal that I am getting at receiver side. So that means there is less error. And resolution is high. Resolution means the way that we see our signal. Resolution means if I will tell in terms of video, that is resolution some 16:9, or so that is some you will say that 720p, 1080p, 480p, 360p. These are the one type of that quality. So that resolution means if I will increase the number of n, means my resolution will be high. I will get more clarity, means I will get the exact signal. Now there are certain devices that is called analog to digital converter or digital to analog converter, which will convert my analog to digital signal, that is with a voltage, current or voltage to number of bits, or a digital to analog signal, it will convert number of bits into my current or voltage. Okay, now let's see the amplifier. What is amplifier? It is an electronic device that can increase the power of a signal. If you will see, if you will remember that in transformer, what does a transformer do? It is just convert our voltage V1 to V2. Either it will increase my voltage or it will decrease my voltage. But a amplifier, it is nothing but it will increase my power. That is in terms of voltage and current, but it will increase my power. Okay. So it is a two-port device that will supply to increase the amplitude of a signal, amount of amplification. Okay, that is how to find this amount of amplification. That is in terms of gain. Gain means output upon input, that is output voltage or output current or output power divided by input power, current and something. So there are three types of gain. One is voltage gain, one is current gain, and third one is a power gain. So this is the output voltage upon output current. And if you write this power gain in terms of dB, that means 20 log AV. AV is nothing but this AV, which is nothing but V out by V in. And AP power gain, similarly P out by P in. That is if you convert convert into dB, that will become 10 log AP. Okay. Now, what is the circuit symbol for an amplifier? So this is the circuit symbol of an amplifier. This is the two way to represent. I said this is a two-port amplifier, is nothing but a two-port device. If you see, it is a two-port electronic circuit. So two-port means this is one port, this is one port, and this is the input port, this is the output port. Either you can represent like this, or a input terminal, output terminal, that is a common terminal. This is called common terminal amplifier. And this is the output versus input characteristic of amplifier. So if you see, this is the Vi, this is the Vi input, means if I will give some input over here, it will multiply some AV, that is the gain of this amplifier, it will give me output. So what will be my slope, which is nothing but AV upon 1. Okay. If you remember this is the one important point you remember, when our AV and AI or AP value that we are getting from these three. If I am getting this from these three, if the value is coming negative, it means my signal, output signal is just 180-degree phase shift of my input signal. If the negative sign comes over here, and if my negative sign is coming in this gain, that is under dB, that means the signal is attenuating. Okay, that's the same thing that I wrote over here. Now we'll see the amplifier power supply. Okay, these are the amplifiers which I have not shown the power supply. Each and every amplifier need a power supply to operate, but this amplifier have not shown this power supply just to make the circuit simple. But you remember, every power amplifier need two power supply to operate. These are the V plus and V minus, or I can say VCC minus VE, along with input signal and output signal. These two power supply needed. Okay. So what will be the total DC power supply, which is nothing but VCC IC, because of this DC. This is the VCC voltage, which is nothing but VC into IC will be the power, and VE IE will be the power. So these two power combined to give a power DC power. Okay. As this is the one type of input, that is the power supply given to this amplifier, and this is also one type of input. So these two input given, that is PI and PDC, it will give me an output power that is equal to across the load, and some will dissipate, some power will dissipate in terms of heat. So this is the power DC and input, that is the two power supply that are given into this amplifier, and this is the output power, and some dissipation will occur across this, inside this. Okay, so what will the efficiency, which is nothing but load power, this load power divided by this PDC. Why? Among these, this dissipation power is very less, and this input power, which is very small. That means we are only taking the value of load power and this DC power. So our efficiency is, we will found the efficiency in terms of that. Then amplifier saturation. So what does mean saturation? It is not like that we will supply a heavy amount of voltage that our amplifier will work. Amplifier has some certain limitation, that you will see, if this is my input, if this blue one is my input, I am getting a bit high output multiplied by this input times gain, it will give me some output. But as I am increasing my input with a value higher than this is the limit. If you see, this is the limit, this, then my output is clipped. You see, my output is coming only like this. It is clipped, this part is clipped. This is called clipping circuit or limiting circuit. That means my input should be limit with this value. If my input will limit this value, then I will get a exact output, and if I will increase my input beyond this, then my output will be clipped. That's why the amplifier has some saturation, means till this point we can give our input. So after this is the linear characteristic, but after that our amplifier will become saturated. So what is this value? This is called L plus, this is the L minus. These are the saturation level. Okay. And after that we read, there are certain notification that we will see in our throughout the syllabus, that is small I, small t. It means the instantaneous component, total instantaneous component, that is equal to small I subscript capital C, and some direct component that is nothing but IC or VDC. Some incremental component is nothing but small I, small c. So suppose a sinusoidal signal is given, so what will be this amplitude? It is the same as this DC. So it is capital I, small c. And some power supply, that this amplifier need two power supply, which is not VCC and VE. These will be written in terms of capital V, capital C. Okay. Then the circuit model. How an amplifier can be represented in terms of model, that is the circuit model. Don't confuse between the circuit model and circuit symbol. Okay, this is only the circuit symbol, and this is the circuit model. So in the circuit model, I have to apply a voltage source with some series resistance with this input resistance, and there will be one voltage control voltage source. It is a resistance and a load resistor is there. What will be the function of this VRI input resistance? Is nothing but it will become a power divider, voltage divider. This voltage will divide across these two resistors. So to get maximum input, this is nothing but my input voltage. To get maximum input voltage, my RS value should be less. If this value will be less, then I will get maximum Vs over here. If I will get maximum Vs over here, then this voltage is applied. Since it is a voltage controlled voltage source, it is a voltage source which is controlled by this voltage. So this is nothing but a V naught into Vi. So if my Vi will increase, then a V naught into Vi will increase. Again, at my output side, there are two resistors, one is here, one is here. So it will also act as a voltage divider. So how to get a maximum output voltage? There is nothing but main supply voltage multiplied by this resistance divided by sum of the resistance. So if my R0 value will very less. If my R0 value will less, then I will get maximum voltage over here. That means at my output I will get maximum output. So for the total circuit, what are the conditions? My RS value should be very less. Sorry, my R input value should be very high. In either way you can say this value is less or this value is high. Only here we are talking about input resistance and output resistance. So my input resistance value should be very high and my output resistance value should be very less. Then only I can get maximum output across my load, that is nothing but the Vs. Okay. So some ideal voltage, it is one type of, it is a voltage amplifier because the output is a voltage, the input is also a voltage. Okay, there are some other types of amplifier. There are current amplifier, transconductance amplifier, transresistance amplifier. Depend upon the input and output. Here, since both are input, output are voltage, it is called voltage amplifier. So for an ideal voltage amplifier, my R0 value should be 0 and my load value should be high. It means ideal means this value should be very high and this value should be very low. If this value is very high, maximum voltage will come over here. If this value is very low, then maximum voltage will come over here. That we need. Okay. So this is how to find the gain. The gain is nothing but V out upon V input. Okay, using this voltage divider, we can find our V output in terms of AV naught Vi and AV naught Vi from here Vi in terms of Vs. This is the voltage gain, which is nothing but V out upon V input. How to find the total gain, which is nothing but V out upon Vs. That means V out upon V in multiplied by V in upon Vs. You see, this is nothing but V out upon V in. This is the gain of an amplifier. Sorry, this AV naught with this value. It is not, this two include give me a V out upon V in. But if I will multiply V in upon Vs, then this term will come. Then the whole term gives me a value V out upon Vs, the overall gain. Okay. This is the voltage amplifier. Now the cascade amplifier. Cascade means this is the one amplifier stage, they are combined with a parallel connection. Cascade means parallel connection. You see, each and every stage has some different function. If I want this input resistance should be high, so this amplifier will work. Suppose if I need a output resistance value low, so this amplifier will work. So each stage, if in our some application, we need various types of stages, various types of application that some amplifier should work on high input, low output, gain should be 1. So accordingly, we are going to cascade our various amplifiers. Okay. So there are, as I told just before, there are 4 types of amplifier based upon my input output. Voltage amplifier means input voltage, output voltage. Current amplifier means input current, output current. Transconductance. Conductance means I by V, means my output is current, input is voltage. Transresistance, it means output is voltage, input is current. So accordingly GM, which is nothing but my short circuit transconductance value, GM, and RM, which is nothing but open circuit transresistance value. Okay, from this diagram we can find these 4 values. Here is just a comparison of these 4. There are 4 type of amplifier that we will see. So this is the voltage amplifier. The second one is current. You can see it is the current. Output is also a current. So in third, if you will see the gain parameter, which is nothing but output upon input, and if you will see the gain for second case, which is nothing but output current upon input current. There are some certain conditions we have to do. For this case, my output current should be 0, means my load should be open. Second case, my output should be 0, it means V output should be 0. And the third case, the V output should be 0. This is the current upon voltage. So in this way, we can find the 4 values: RM, GM. This is short circuit current gain and open circuit voltage gain. Okay. So this is all about our first chapter. Now we will see the operation amplifier. So what is a op-amp? Op-amp means operation amplifier. So it is an amplifier which will do some operation. So first let's see what is ideal operation amplifier. So ideal operation amplifier means what is a op-amp? It has some 2 input side and 1 input terminal, output terminal, and it has 2. It need 2 battery source to work. This is VCC and VE. Okay. So there are, what I am seeing, we are seeing here 5 terminals. So along with the 5 terminals, there are some other terminals that we are not seeing over here, or we have not indicated over here. I told before, that is the frequency compensation terminal, and one is offset nulling terminal. So frequency compensation is used to this obstruct this oscillation. We will see later that in later video, that after completion of our basic electronics syllabus, these are the topics that we have not covered in our syllabus because it is not there. Just for now, just remember there are 2 other terminals are there, frequency compensation and offset nulling. These 2 are included along with the 5 terminals. So this frequency compensation is used to avoid this oscillation. And why this nulling, offset nulling is there? Okay, if you will see the condition when my VID, which is nothing but difference between 2 input voltage, how I will get my V output, which is nothing but difference between 2 input voltage multiplied by the gain, it will give me the output. So if my VID will 0, that is the difference to input will be 0, that is 0 multiplied with the gain of this op-amp, it will give me a value, output will be 0. So this is V output will be 0. But there are certain cases when manufacture process, some difficulties are there. So this VID, which is not 0, at that case also my output I am getting, what I will get, I get not my output as 0. So for that reason we have to use a offset nulling so that it will maintain that stability, that if VID will not 0, then also my V output should be 0. Okay, these are the 2 components that we will use. Now we will see some properties of an ideal op-amp. So op-amp is designed, it will take the value of V input of one terminal, V output, sorry, second input of other terminal, and will take the difference and multiply with the gain with the op-amp. This is the V2 minus V1. V2 is nothing but the positive terminal of this op-amp. This is the negative terminal. Okay, so my V output, which is nothing but A times, that is gain, open loop gain of V2 minus V1. And this is the ideal op-amp. Ideal op-amp means, in ideal op-amp what we will do, we will think that op-amp will not draw any current. That means the input current to this op-amp is 0. Okay, if input current is 0, it means what, then at that case what we will see, our input resistance, that is also infinite. Infinite input resistance means it is open circuit or not. If my resistance whose value is infinite, it means it is obstructing each and every current, that means current equal to 0. Current 0 means infinite input resistance. Okay, at secondary side, how I am getting my output? My output is nothing but A into V2 minus V1. But this output which I am getting over here, that is the voltage over here, that is the voltage control voltage source, A into V2 minus V1. It means there are no other component present over here. It means my op-amp, it has the output resistance of value 0. Okay, when output resistance value will be 0, it means it is short circuit. It is short circuit over there. So short circuit means it is easily allowing current. That's why I am getting the same voltage, whatever the voltage that is present over here. Okay, so based upon that, whatever my output is nothing but A into V2 minus V1. So if you will see this V2, which is multiplied by a positive sign, and V1, which is multiplied by a negative sign, that's why op-amp, it is in the output is the same phase with my V2, means output is positive, V2 is positive, and my output is positive but my V1 is negative. It means my input V1, which is in phase, sorry, out of phase, and my V2 is in phase. That's why V2 terminal is called, that is the second terminal. The second terminal is called non-inverting terminal. Okay, and since the negative sign is multiplied along with my V1, it is called inverting terminal. Okay, now my op-amp will respond only to the difference between 2 inputs. It means if I will take a V1 and V2 and the both signal having different value, then my output, I will get my output. And if the V2 and V1 both are same, it means that are common in both input, then what will do, my input output will reject. That means a op-amp will reject the common input. That is called common mode rejection. It means the common signal present between 2 input, it will reject. Okay, it means my op-amp has 0 common mode gain. Since there are no common signal at my input side, then at my output side I will not get any output. It means my output by input, which is nothing but 0. That means 0 common mode gain and infinite common mode rejection. It means it will reject each and every signal that is common in both input. If that is common, it will reject. That's why infinite common mode rejection. So what is our op-amp? Op-amp is a differential input, single-ended out operational amplifier. It is a differential input. We are taking the difference, and a single-ended output. At single end we are getting the taking the output. Okay, so remember these are some characteristic of op-amp. Some practical cases we have to, ideal for ideal op-amp we have to take my input resistance would be infinite, output resistance would be 0, current that is drawn equal to 0, and we'll see the gain equal to infinite. So there are certain case that you have to remember. Now, one point you see, that is the infinite bandwidth. I am not covering each and every point because in the video I have said each and everything. Just for a revision I am doing this. So infinite bandwidth means if a signal having 0 frequency, that signal will be amplified to a high value. And if a signal having a frequency value of very high frequency, that signal will be amplified to the same level. It means from 0 frequency to infinite frequency, my signal is amplifying with the same value. It means it has a bandwidth which is nothing but upper frequency minus lower frequency is the same. That is the infinite bandwidth. So we can represent our two signals, that is one V1 and V2 in terms of common mode signal and differential signal. So common mode means it is nothing but average of two signal V1 plus V2 by 2, and the difference signal means it is a difference of two signal. So if the two signals V1 V2 are given, we can write that two signal in terms of VICM and VID by 2 by VID by 2. If I will take my voltage at one terminal, that is nothing but VICM minus VID by 2. So this is my V1, VICM minus VID by 2. And if we will come to this path, VICM minus VID plus VID by 2. So this is the voltage at second terminal. Now there are two type of configuration. One is inverting configuration, second one is non-inverting configuration. So what is inverting configuration? When our input that is given to the inverting terminal of op-amp, that is the inverting configuration. So this is the feedback path, which is nothing but the negative feedback path. Okay. So now here according to, we have to assume that since this is ground, this is 0 voltage. According to the virtual short, these two voltage are 0. This is also 0 voltage. So let's take for ideal condition that when my gain is equal to infinite, at that case I will get my V out upon V in, which is nothing but R2 by R1. Okay, that we will see in later case how it is becoming R2 by R1. Now, what do you know? This is a ideal op-amp. Ideal op-amp means the gain should be infinite. If gain equal to infinite, then my output, which is nothing but gain times VID. So V2 minus V1, which is nothing but output upon gain. Since gain is infinite means this output is 0. It means my V2 by equal to V1. These two voltages are same. By that concept, we are saying that if this is 0 voltage, this is also 0 voltage by virtual short. They are not actual short, but they are virtually short for ideal case. Now, what we found that our gain, open loop gain, which is nothing but minus R2 by R1, that is the feedback path resistor divided by the input resistor. So this is the feedback path resistor, this is the input resistor. Okay, since at the gain the negative sign is coming, it is called inverting configuration because of this negative sign. Now it is what we took that for our op-amp that the gain is infinite. Now let's take a op-amp whose gain is not infinite. So it is an ideal op-amp. All condition, R input should be high, R output should be low, all conditions are there, only the gain is finite. So if we'll see the derivation that we did in the video also, and here also we did, that our get, what we will get our gain is nothing but R2 by R1, 1 plus this value. It means it is depend upon A. As this A is finite value, it means this gain will depend upon my A, open loop gain. So for our practical case, that we have to assume this 1 plus R2 by R1 value should be very less than A. If this will be the case, 1 plus R2 by R1 will be very less than A, then what will happen? This term, this will become 1. Since this value is A is very high, than 1 plus R2 by R1. So something upon very high means very low value. 1 plus something very low means this value is approximately 1. It means my gain is nothing but minus R2 by R1. That we got for our ideal case. Okay. So for practical case also, we have to keep this point in our mind. That's 1 plus R2 by R1. We have to choose our R2 R1 value in that way. Now, what will be the input and output impedance for a resistor? For ideal case, the input impedance is infinite, output impedance is 0. But here, we know what we got. Our R2 by R1 is nothing but the gain. But if you see from input side, from this input side, what is my input impedance that is seen over here? If you see connect a voltage and current source, if you see the impedance from this side, which is nothing but R1. Okay, it means my input impedance is R1, so that should be high. But our op-amp should work properly. It means my gain should be high. So gain should high means my R2 by R1 value should be high. So this is the gain formula, which is nothing but R2 by R1. This value should be high. But here what I am getting, that my input impedance should be high, means R1 value should be high. But since these two are contracting, we have to focus in this point, because our op-amp should work as an amplifier. That means this R2 by R1 should be high. It means my R1 value is less. It means for our inverting case, my R input, which is nothing but very low R input. Okay. But R output is 0 because there are no other component that are present over here. It means my R output is 0. Now this inverting amplifier can be act as a summing circuit. What does mean a summing circuit? Means at the input side I can give various types of input, and accordingly my output will be the sum of 3 input. We have already done this derivation. This is nothing but first input V1 and RF, this feedback upon this resistance, plus RF by R2 into V2 input, RF by R3 into V3. So similarly, if I can add, this is one type of. And second type also, if I will connect the same part over here and I will connect like this, so it will, here you can see the signs that are negative for all cases. It is also negative, it is negative, but it is negative. But in some application I need a positive coefficient. Then I have to connect 2 op-amp in this way. Then I will get, you see here 2 inputs are positive, 3 inputs are positive, and the 1 input is negative. Okay, like this way we can arrange our op-amp. Now the non-inverting case. So non-inverting case means the input should given to the non-inverting terminal, that is the second terminal. Okay, for ideally let's take this is ideal op-amp and gain equal to infinite. If gain equal to infinite, then V2 minus V1 equal to 0. Since gain is infinite, this is 0 means my V1 V2 both are same. So this is V input, this is nothing but V2, which is V input, this is also V input. Okay, and similarly if we will derive our gain, that is V out by V input, is nothing but 1 plus R2 by R1. Okay, 1 plus R2, for in inverting case it is minus R2 by R1, here it is 1 plus R2 by R1. Since the positive sign it is coming, it is called non-inverting configuration. Okay, now similarly here there is no effect of open loop gain, that is A. In previous case also there was no dependency, but if you will add the dependency of A, then we will see our gain which will come if we will derive the same way without taking this A is finite value. This A is, it is finite, it is not infinite now. Okay, so you will get a output G gain which is nothing but 1 plus R2 R1 by this value. Similarly in previous case we got minus R2 by R1 divided by 1 plus this same. Why this path is same? It is the same closed loop feedback circuit we are using for inverting case or non-inverting case. This is the same. Here is a resistor, here is resistor. For inverting case also this is the same. Okay, that's why the denominator part is same for both cases. Here similar for the previous case, this value should be very greater than A. If this value will very greater than A, then this value will become very less, negligible to 0. 1 plus some value very close to 0 means this value will become 1. So some value upon 1 means this is the value that will get output. It means for our, to minimize the means our G should not depend upon A, because A is a very infinite value that we don't know the value. So we have to make our op-amp in such a way that this G should be independent of this A. Okay. Now how to find the gain error? That is gain when infinite, when it is finite A, and gain when it is infinite A divided by gain at infinite A. So you will see this is the percentage of error gain. Everything that we have already done in our video, but I am just revising some terms so that it will become easy for you. Okay, here in this case our input is infinite, our output is 0, because for inverting case there was a condition of minus R2 by R1, so we can't increase our R1, but here there no such criteria is there. Okay, so here if I will make a op-amp whose R1 value is 0, you can see, sorry, R1 value is infinite, means it is open, and R2 value is 0, it means it is short. R2 value 0 means no resistance, maximum current flow in a short circuit path, that's why it is short circuit. R1 is infinite, it means this is open circuit, maximum resistance is there, means no current, that's why current is 0. If I will make a circuit whose R2 is 0 and R1 is infinite, it will become a unity gain buffer. It means it is a amplifier whose gain will be 1 and my output will follow the input, that's why it is called follower amplifier. Okay, so this is the equivalent model of the same one. If you see, there is no R1, since this R input, which is nothing but input impedance, is nothing but R1 value, which is infinite. Infinite means open circuit. Here you see the R2 is 0. This is the equivalent model. Now the difference amplifier. As we have just read before, the common mode signal and differential signal, our input, whatever that we are getting at output, that is the combination of two, both differential input and both of common input. But at our output, the common modes are rejection ratio is very high, that's why not getting in common signal. Only we are getting because of different signal. So that a term called common mode rejection ratio. It will define that as op-amp how much it can reject. That is 20 log AD upon ACM. AD equal to gain of difference amplifier. ACM is the gain of common mode signal. Okay. Now there is one instrument amplifier. These are the extra that I did for you. Okay. Now it is the integrator and differentiator. Our op-amp can be used as an integrator differentiator. If I am giving an input terminal Vi and I am using a capacitor over here, then this resistor capacitor combinedly give me an output which is nothing but the integration of my input. You see here the output which is nothing but integration of input in terms of RC, that is the time constant of RC circuit. Okay. Similarly, our op-amp can use as differentiator. If you see, if I connect capacitor over here and resistor over here, my output, that will be the derivative, that is differentiation of input. So these are the some signal that I have used. If I will give a sinusoidal signal to my input, then what will the differential amplifier, this differential amplifier will give me? It will give me a sinusoidal signal. Since for square wave, it will give me impulse. Okay. So this is the end of our second chapter. Now we will see the semiconductor diode. So in a semiconductor diode, first we will see some properties of semiconductor, then we will move to the diode. So before going to the semiconductor, let's see some, that is the three type of material depend upon the conductivity. So one is conductor, that is semiconductor, third one is insulator. So for these are the some properties. It is high for conductor, the conductivity is high, and for insulator it is low, and for semiconductor it is the moderate value. And for forbidden gap, which is nothing but the energy gap between two conduction band and valence band, here there is no gap, so easily electron can move from conduction band to valence band, that's why it conduct high current. And for insulator it is a very high value of gap is very high, so that electron can move from conduction band, valence band to conduction band, so that's why it won't conduct any insulator won't conduct any value, any current. Okay. And for semiconductor it is a moderate value. Similarly, these are some properties that you can see. Okay. Now there are two types of semiconductor depend upon the concentration. So one is intrinsic, one is extrinsic. Intrinsic means it is the pure form of semiconductor. Okay, so there are two types of in which we can distinguish our semiconductor. There one is single element semiconductor, one is compound element. Single element means it is only silicon or germanium. Compound means it is a combination of two, that is gallium arsenide, indium phosphide. Okay, or silicon carbide. It is like that. So in pure semiconductor, this silicon, you can see they are arranged in a crystalline form, or there is silicon made a covalent bond with its nearing atom. So it is a covalent bond. So when there is no temperature applied, then these bonds are very tight. Okay. So in this case, there is no free electron. Bond are tight means electrons are tied with each other. No free electron means no current conduction. It means it behaves as an insulator for zero temperature. And at room temperature, as we increase the temperature, these covalent bonds start breaking. Start breaking means an electron will generate from here. So you can see at room temperature, that is some thermal temperature. After giving some room temperature, 25 degrees Celsius or 300 Kelvin, what will happen? This thermal generation means applying of temperature. A covalent bond will be broken, so electron is freed. It can wander away from its parent atom. It means when temperature is applied, this electron, let's take this electron, it is now freed from its parent atom. It will move throughout this crystal structure. Okay, so that it will conduct current. Free electron means it will conduct current. So as we will increase our temperature, what will happen? More number of charge carrier will generate. So when an electron leaves at parent atom, this atom it will leave a hole over here. It will go, suppose here it is a electron, it moves to here. This is the electron. Now here is a hole. So once apply your temperature, electron is generated, means electron hole pairs both are generating. Okay. So that to replace that hole, what will happen? That some neighboring electron that will attracted by the atom and that will filled by the neighboring atom. So what will happen? At that side, at that neighboring atom, there will be one hole. So similarly in the crystal structure, what will get? Will get at final stage, that is either a electron at stage or a hole. So that electron hole will give me the conduction of current. So as we will increase the temperature, more number of electron hole pair are generated. So how much it will generate, it depend upon the temperature that we are giving. So the thermal generation result in free electron hole in equal number and hence equal concentration. The number of electron will generate, at the same time the number of holes will generate. Okay. So the free electron and holes that are randomly through the silicon crystal structure and the process, okay, that is recombination. What is recombination? When an electron is generating and a hole is generating. So to replace that hole, one electron is coming from neighboring atom. That means electron and hole, they are recombining. Similarly, to occupy that hole, again one electron from a neighboring atom, it will come. It will again recombine. So this process is called recombination. So how much it will recombination? Depend upon how much it is generating. The number, more the number it is generating, the more the number they will recombine. Okay. So it is a term, the thermal equilibrium means at a fixed temperature, my recombination rate is equal to the generation rate. The number of it will generate, the number it will recombine. So N equal to P equal to Ni. N equal to number of hole electron, P equal to number of holes, Ni equal to number of free electron hole in a unit volume of intrinsic. Intrinsic means is the pure form of silicon semiconductor. Okay. So for general case, N number of hole equal to number of electron is both equal to number of free electron or field charge. So this, if you can write n into p is nothing but ni square. So what is our ni? Is nothing but b t 3 power 2 by 2 e power minus eg by 2 kt. B is the material dependent constant, t is the temperature, eg is the band gap energy, k is the Boltzmann constant. Okay. So for our ni value for a room temperature, its value is nothing but 1.5 into 10 to the 10 carrier per coulomb. Carrier per centimeter cube means for a unit volume we are measuring the charge. That is the carrier per centimeter cube. Remember this value 1.5 10 to the 10. Now let's see the extrinsic. Extrinsic means it is the impure form, because this much ni value is not sufficient for a silicon atom to conduct current. Because a silicon atom to conduct current, it need around 2 into 10 power 20. That much amount of carrier per centimeter cube needed in a unit volume. If that much amount of charge carrier are present, then only it can conduct. But here the value that we got is nothing but 1.5 10 to the 10. That value is very less. That's why we are going to increase our concentration. How we can increase our concentration? We have to add some impurity, that is called extrinsic or doped semiconductor. So there are two types of possible. One is p type, one is n type. So how p type is formed? When silicon is added to the trivalent. Trivalent means it is outer shell, there are 3 electrons, and here outer shell there are 4 electrons silicon. So 4, here 3. That means here is a one shortage of electron. So p type is a shortage of electron. Shortage means it will accept from somewhere. That's why for p type the Na, that Na term comes here, Na. And how n type is formed? When silicon is added to the pentavalent, means it here it is 4 electron at valence shell, here it is 5 electron at valence shell. It means it is a excess of electron. Since it has a excess of electron, what it will do? It will donate. That's why we will call it a Nd. It is the donor concentration, it is the acceptor concentration. Okay. So you see, let's take for n type. N type, there is an extra electron, 5th electron. So the positive charge associated with the phosphorus atom is a bound charge that does not move through the crystal, so no holes are created. What will happen in this n type? 4 electron of pentavalent and 4 electron of silicon, neighboring silicon atom. They are already occupied with a covalent bond. 1 electron is extra. That electron can be replenished by this hole, because there is no positive charge present at the outside. Because whatever the charge that is present inside the nucleus, that is inside the nucleus and that is bound, so they can't move. Those charges can't move. That's why here one extra electron is there. So here the Nd, which is nothing but the donor concentration. So here Nd, since Ni is the normal for silicon, that is the concentration, and here we add some impurity. Our Nd value will be definitely higher than this Ni. Okay, this is the derivation, nothing but for n type material, number of holes. For n type material, number of holes. Now n type material, number of electron, which is nothing but n into p equal to ni square. That's why we did this derivation, and we got our Pn equal to ni square by Nd. Okay. Since this is the n type, our electron will be measured charge carrier, because here you see, here is one silicon, here is one pentavalent impurity. This is only for one crystal, silicon. There are millions of pentavalent impurity and millions of silicon. It means here is one extra electron is there, and there might be another structure where is an extra electron there. So if I take the crystal, so the crystal will be full of electron. So that is the electron as a majority charge. But there are also minority holes that are the less. Minority carrier means these are the less carriers. Now for the p side, so this is the derivation that we did. Our Pn is nothing but ni square upon Nd. Okay, that was the n type. Now for the p type, what will happen? Here there is a shortage of electron, means it is the it will accept Na, the term will come over here. So this is the Na. Okay, now ni square upon Na equal to Np. This is the what? Holes. This is the number of electron at p side. This is the number of holes at p side. Pp means holes at p side. This is the holes electron at p side. So this minority here minority charge carrier is nothing but my electron. So this minority charge carrier, this is the minority charge carrier, because number of holes at p side. Holes means these are the minority charge carrier, that will depend upon the temperature. That is nothing but ni square. You can see the formula for ni square, which is nothing but depend upon temperature. You see this Ni is depend upon temperature. It means here this Np, that is the minority charge carrier for p side, it is also depend upon temperature. Similarly for this Pn, which is nothing but number of holes at n side. So here holes are the minority charge carrier for n type, that will also depend upon the temperature. Ni square means it depend upon the temperature. Okay, now we will see the current flow in a semiconductor. In a semiconductor there are two type of current flows. One is because of drift current and second one is because of diffusion current. So how drift current form? Because of electric field. We will see that how applying electric field we are producing current. So remember, for drift current it is formed by the application of electric field, and how diffusion current formed, that is because of the carrier concentration. Okay, this is the derivation that we did, how electric field is generated, and if this area is given in an area, what will the current, which is nothing but this AQ P Vp drift, which is nothing but drift velocity, because some electron hole they move with a velocity that is the drift velocity, and drift velocity is nothing but mobility into electric field. So you see the current which you are getting, that is the drift current, is because of this electric field. Okay, so this is the current density which will divide by I divided by A, will get a current density. So at our final for both electron hole, what we will get? We will get our current density is nothing but Q into N mu N plus P mu P whole into E. This is the electric field applied. This is the mobility of holes. This is the mobility of electron. This is the mobility of holes. If you remember that I said before, the mobility of electron is much more than 2.5 than holes. Means in a crystal, electron can move very easily. So we know this J equal to sigma E. So if I compare this, E is there, E is here. The sigma is nothing but this conductivity. Okay. So the conductivity that we can found from this derivation, or in terms of resistivity 1 by conductivity. Now the diffusion current. What happened? Since there are a crystal, the electrons are more over here and less this side, or holes are more over here or less this side. So because of their carrier imbalance, what we are going to do? Should be diffusion. Diffusion means electrons should flow through this side, holes should flow through this side, so that it will maintain an equilibrium. As this electron hole, they are flowing from one side to another, so they are decaying. Because of that, there is a current conduction, Jp. Okay, that is nothing but rate of change of this concentration change multiplied by some diffusivity with some charge of each electron. Similarly for Jn we will see. Okay, so Jp here, why this negative is there? We know current flow in the same direction, that is because of holes. Okay, here you will see whatever be the flow of hole, here the slope is negative. So what will the dp by dx value? This value will give me a negative value, the dp by dx. So this negative into negative, it will multiplied to give me a value positive. It means the current because of holes because of holes is positive. Okay, that's why this negative is there, so that it will make this negative to become plus. And for electron, you see this is nothing but q dn by dx, because for electron, if electron move this in this way, my current will flow in this way. It means electron and current both are opposite direction. So this Jn is nothing but q dn by dx. So this slope will give me a negative value. That means my current will get a negative value. Okay. So this is called Einstein equation, dn by mu n equal dp by mu t equal to Vt. Vt is called thermal voltage. So remember this thermal voltage for room temperature 300 Kelvin or 25 or 27 degrees Celsius. Vt value is 25.9. Or in our calculation we are taking 25 or 26 for easy calculation. Now we are interested to apply the voltage to this PN junction diode. Okay, if we will apply voltage, then what will happen? There are one that is for, let's see what is diffusion current, how diffusion current is formed. Here at condition when there is no applied voltage, means we have not applied voltage. This is the P side, this is the N side. P side is formed when silicon is added to the trivalent impurities. Okay, shortage of electron means there will be less electron, more hole. So you see here there are more hole. These red dots are the holes. Okay, so in N side, this is the form by silicon with a pentavalent. It means excess of electron. You see the negative sign, which are nothing but the electron. Okay, so these electrons are majority charge carrier, but there are some minority charge carrier also. These holes, 1, 2, some less holes are there. Here this P side, electrons are minority charge carrier that are there. So what are these rounded side, which is nothing but the Na or Nd that is present. In P side, what is there? It will accept, since it is a shortage of electrons, so Na is there. Accept means I am returning is a negative sign, means it has less power. Or it is poor, in terms of it is poor. That's why bound charge, but they can't move. Only these holes and this electron they can move. This electron or these holes, they can only move. But these are the bound charges, they can't move. Okay. Now, because of the concentration of hole is high, this side hole having maximum number of hole, this side less number of hole. So carrier in concentration, so carrier will concept to make this stable, the holes will start to flowing this side. Similarly, here is more electron, here is less electron, so electron will start flowing this side. So as this electron and hole flow through this junction, they will conduct a current, that is nothing but IT. Since holes are moving to P to N and electron from N to P, that means my current will be from P to N. Okay, so as this hole and electron they are crossing the barrier, these electrons are combining with these holes and these electrons are combining with these holes, so they are removing means they are a recombination. So these holes and these electrons are not present only there. When they will cross each other the junction, so there will be no more electron and free charge carrier. There will be only bound charge carrier. If you will see in this diagram, as they have crossed the barrier, there are only bound charge carrier. You see there are no free charge, no electron, no holes present over here. These electron hole are because of the minority charge carrier. These are the minority charge carrier that I am showing. That is because of thermal generation. But here the diffusion current, that is because of the majority charge carrier, which is nothing but electron hole. And as they cross, they are making a barrier. Barrier means it will obstruct the again flow of any electron or hole. So since here is a positive bound charges, here the negative bound charges, they are forming a potential difference. What they are forming a potential difference. At this terminal there is a potential difference V0. Okay. Now as the electron that are diffused across the junction into P side, they are recombining with other side, and similarly holes coming this side, they are recombining with the holes present over here. So they are, since the recombination, they are become a depletion layer. Okay, that depletion layer is full of depleted of holes and containing uncovered charge. You see, these are the uncovered charge. These are the uncovered bound charges. These are bound, they can't move. Okay, so as there is a carrier depletion in this case, then what will happen? It is called a charge region. You see, here is a plus charge, a minus charge. So it is a space charge region. This region is called space charge region. Or it is a potential barrier that will also form. So because of this potential barrier, there will be an electric field. We know E equal to minus dB by dl. So because of this potential difference or V0, there will be an electric field. Then what will happen? This electric field, they will oppose the another flow of any electron. Already electric field is produced, they will not allow this holes to this side or this electron to this side. Okay, these are the case for this majority charge carrier, that is called diffusion current. As my electric field is much stronger, that means my V0 value is much stronger, they will not allow. So it means my barrier voltage, if barrier voltage is high, my ID will be less. Okay, the second case, which is nothing but the drift current. How this condition arises? This is because of the thermal temperature generation. See, in our crystal there are minority charge carriers that are present. Here, see, here these are the minority charge carriers. Here there are minority charge carriers. So as the electric field that is produced here because of this electric field at the barrier, the minority charge carrier present, this minority charge carrier, they will be swept to holes to this side and electron to this side. So these minority charge carrier will give me a current conduction. That is called drift current. Okay. So you see, when there is no applied voltage, it means whatever the current that I was getting because of this diffusion current, that will be the same that is because of my drift current. Okay, majority charge carrier current, that is the diffusion, and because of minority charge carrier, that is nothing but the drift. When there is no voltage, each current should be equal, the both current ID and IS. So at that case, my ID equal to IS. Okay, so if any case arises when my ID increases, then what will happen? This V0, it will obstruct another flow of electrons, so it will again decrease my value of V0. Now the junction between voltage, the voltage that is developed at this junction, which is nothing but potential barrier voltage, that is nothing but my V0, which is nothing but Vd ln Na Nd by Na square. Na equal to number of acceptor concentration at P side, this is the for N side, this is the intrinsic concentration. Okay, this V0 is called the built-in voltage. And this is the voltage required for PN junction to operate. If we will supply, if you will see in diode section that if this much voltage is applied, then only the diode will work. So this is the V0. Okay, for silicon it is 0.6 to 0.8 or 0.9. For germanium it is 0.3. Now we will see the width of our charge stored. Since it is, here see some charge is stored, and because of that some width, it is the depletion layer which has some width. So now we are interested to find the width of that region. Okay, now for that what we are going to do? We are going to dope one side with more value and another side less value. Here we are interested to make Na bit more doped than Nd. Here see the Na is more doped, means at Na side more number of doping means more number of charge carrier. You see, as compared to this side, here is more charge doping. Okay, so as doping is more, but this width and the concentration of this charge carrier and this charge carrier should be same. It means whatever the charge that is present at P side will be same as N side. It might be a bit long. My depletion region will elongated towards more this N side to maintain the charge equality. But charge density should be equal in both cases. From that charge density, what we found, we did this derivation in our video, that W equal to epsilon 2 epsilon naught by Q 1 by NA 1 by ND into V naught. This W depend upon the potential voltage V naught. This NA and ND is the carrier concentration of P side and N side. This is the permittivity, electrical permittivity of silicon, which is nothing but epsilon R into epsilon naught. Epsilon R for silicon is nothing but 11.7 and epsilon naught value is 8.854 10 to the minus 12 force per coulomb. Okay, now this is the Xn and Xp. What is Xn and Xp? Xn is the length up to which my N side is depleted, and Xp is the length up to which my P side is depleted. And we have already found that Xn and Xc value in terms of W. This derivation already did. Now the charge which is the stored in that region, which is nothing but function of voltage. So this is the derivation. Now here till yet we have not applied the voltage. Now we have started applying voltage. So there are two types of voltage applying. That is, one is forward bias, when I apply a positive terminal to P side and negative terminal to N side, and a reverse bias, forward bias and reverse bias. Reverse bias, positive terminal to N side battery and negative terminal battery to P side. So what will happen in reverse bias case? Our width will be more high because the electric field that was present in no bias condition, and because of this negative voltage applied here, because of that electric field flows in this direction, and because of this reverse negative bias, that is negative and positive, electric field again flow in this direction. So those two electric field add together will give me a more electric field. More electric field means more width. So for reverse bias the width is more. For forward bias, primarily the electric field was in this direction from N to P, but as I have applied a voltage over here like this, positive to P side and negative to N side, my electric field will be moved this direction. So my net electric field will decrease, but it will in the same direction. As this net electric field is decreased, my width will be also decreased. Okay, as the width decrease, my voltage will also decrease. You see, this is the case V naught. This is the red line, which is nothing but no bias condition. When I applied a forward bias, my width decreases. It means my voltage also decreases, which is nothing but V naught minus Vf. This is the forward voltage. And as my reverse bias increases, my V naught plus Vr. Because of reverse bias, my width increases and my voltage potential also increases. Okay, so in this case, since width is more, it will not allow any further flow of current. It means my ID value will be less. So in reverse bias condition, ID value is almost equal to 0, and the current because of the reverse bias is nothing but because of the minority charge carrier, which is nothing but my diffusion current, or later we will see the saturation current. Okay, and when forward bias, since this width is very less, electron and holes can easily transfer through this junction, so the current will increase. So my total current is because of maximum of current is because of this ID, that is the drift current. ID means drift current, IS means diffusion current. This is the because of majority charge carrier, this is because of minority charge carrier. And now we will see the current and voltage relationship. That we will see after this. You can see this is the relation between current and voltage. I, that is the current of this PN junction, is nothing but function of voltage applied, V. For that we did a long expression, because how to find this current? Current is nothing but J times A, and J means that is the current density. How to find this density? Which is nothing but two. One is diffusion current, one is drift current. And you see, this is the formula that we read. This is the Q dP dN by this, like this. For that we need concentration. That's why we are interested to find the concentration present over here. First we will find the concentration, then we will, using this formula, find the density, and after the density what we will do? We will find the current. Okay, so you see here I is nothing but Is e power V by Vt minus 1, where Is equal to this much value. This value here, Is is a dependence on temperature. Ni means dependence on temperature. Okay, so this is the exponential curve. It means if I draw in forward bias, this will be the graph. My output, if I will increase my voltage, my current will increase in an exponential way. This is the exponential way it will increase. And for reverse bias, since this V is in terms of some voltage of Vt, this value will become 0. My I will become minus Is. So you see, this is the become value minus Is. That is the saturation value. That's why it is called Is. S means saturation. Okay, and remember this Is is a dependency of temperature. Now junction breakdown. As I said, till this point there was the voltage applied over here, my current was saturating. But after, as I increase a bit higher value than this, what will happen? My junction will break down. So as my junction will break down, there are two conditions. One is Zener effect and one is avalanche effect. So because of this two conditions, Vz value is less than 5 volt, then Zener effect. Vz value greater than 7 volt, then it is avalanche effect. And if it will stay in between this, it can be any, either Zener or avalanche. Okay, So in Zener effect, what happened? Because of this electric field, more number of electron hole pair generated, and this electron hole pair will drive me a reverse current, so that my current will increase. It is a negative temperature coefficient. Negative temperature means if I will increase my temperature, then my voltage required for this Zener diode is very less, less as compared to the previous one. Okay, so Zener breakdown is because of the effect of electric field when applied. Then because of high electric field, more number of electron holes are generating. And for avalanche case, it is like the kinetic energy, that one electron is strike with the another atom and it is producing 2 electron, and like this way more number of electron hole pair generated, and more electron hole pair means more current. That's why the current that is increasing at a high rate just after this value. Okay, and it is a positive temperature coefficient. It means if I will increase my temperature, I have to increase my voltage also. Now the effect of capacitor. Effect of capacitor in our PN junction diode. There are two types of capacitor. One is the depletion, or that is called junction capacitor. Second one is the diffusion capacitance. So the depletion or junction capacitance, that is because that happen in reverse bias case. The charge stored in the depletion region, and the Cj, which is nothing but Cj naught 1 plus Vr upon V naught. You can see over here. This Cj is function of reverse bias voltage Vr. And for graded intakes, we have written this. Here the power is nothing but 1 by 2, but some application which need a m value some other value 1 by 3 in range between 1 by 3 and 1 by 2. So our Cj is nothing but Cj naught 1 plus Vr upon. This is the charge stored in the depletion region or the junction capacitance, which is a function of Vr. Okay, reverse bias voltage, and this m is called the grading coefficient. Now second one is the diffusion capacitance. As there is a carrier change in the concentration, because of that there will charge will vary, so accordingly my diffusion condition arises. Here this is the region, because of the concentration we will find our charge concentration, which is in a Pn. Here it is a Np, and for that case my charge, which will be a function of, you see over, this is the charge which is a function of current and the time constant. The time constant means the rate at which the charge they are decaying. Okay, for electron and for hole both case we can find. So what we will find? Our charge, which is nothing but, this is the charge which is nothing but tau t upon Vt into I. So this is the forward bias current, this is the temperature Vt, which is nothing but 25 millivolt. This is the total time constant. Okay, so this is applied, this diffusion capacitance applied for reverse bias. No, sorry, for forward bias, because for reverse bias this value is 0, and that junction capacitance applies for reverse bias. Now the ideal diode. These are the topics that we read just in 3 to 4 latest video. So for ideal diode, this is the Vi characteristic, means for negative half of the voltage it is 0, and for positive half at just internal current is a maximum value. Okay, for forward bias it is short circuit, and for reverse bias it is open circuit. Okay, and this graph between I and V is called the piecewise linear. It is not exact linear, since it is straight line and straight line. These two characteristics is called a piecewise linear. Now the application diode is nothing but rectifier and logic gate. So rectifier means if we are providing some input, our output it will rectify. You see here it is the positive up, and the rectifier, what is the function? It will convert AC to DC. Here is the AC sinusoidal signal, and by using this circuit, diode and resistor, we will get our output like this. Okay, and after applying this circuit into a filter, we will get some different output, and again applying this filter into a voltage regulator, we will get a constant DC value. So this rectifier is a fast process to convert AC to DC. Okay, so this is the V versus I. Whatever the input that we are giving, we are getting the same output for positive half. For negative half, it is reverse bias, it is not working. Okay, this is the half wave rectifier. We can use also this full wave rectifier. We will see here we have taken the ideal diode. That's why the output is coming at an instant applying the input. And this diode can be, this application of diode, this diode can be used as a logic gate. Here you can see this is can act as a exclusive, or this is can add as an exclusive AND gate. AND means the output is nothing but dot product of 3, means multiplier. It is nothing but summation of 3, output equal to A plus B plus C. Okay, so this is the terminal characteristic of junction diode. So this is for the forward bias. Here it is the graph between V and I. If we are going to expand this part and compressing this part, we are going to compressing this part and expand this part, our circuit will look like that. Okay, then we can easily examine each and every. This is the forward bias condition, this is the reverse bias condition. For forward bias, after some voltage the current start conducting, and till this value my output is 0. For reverse bias till some voltage my output is saturation, and after that it is the breakdown region. Okay, since there are three regions, forward bias, reverse bias and breakdown. So for forward bias it is the exponential curve, that is current in terms of exponential voltage. Okay, just remember here IS double for every 5 degree rise in temperature. For forward bias my IS, which is nothing but this IS saturation current, it rises for every 5 degree rise in temperature. As temperature increases my IS become doubles, and this is the derivation that we get in forward bias. My V2 minus V1 is nothing but 2.3 Vt log I2 by R1. If I am applying 2 current, accordingly my 2 voltage will be in terms of this 2.3 Vt multiplying time log times. Okay, so in forward bias condition, our voltage drop across the diode, which is decreased by approximately 2 millivolt for every 1 degree rise in temperature. Here the condition that we get, the current doubles. Here the current double for every 5 degree rise in temperature. But here, as the current is fixed, my voltage drop by 2 millivolt if I will increase my temperature to 1 degree. And that is for the reverse bias condition. Reverse bias condition, since where my reverse voltage, which is nothing but, where is that diagram? We got our output current, which is nothing but IS into e power V by Vt. Let's take this example, it will be enough. Okay, let's take this one. If this is the current, okay, if my reverse voltage will be much some times Vt, then this value will be negative. E power negative means this value seems to be 0. So this I is nothing but minus Is. So that is the case when my I is nothing but minus Is. Okay, and here the current is constant. You can see from the diagram, the current is constant for reverse bias condition, and it is saturation of a value Is. And here the current doubles for every 10 degree rise in temperature. For forward bias, the current double every 5 degree rise in temperature, but for reverse bias, the current double every 10 degree rise in temperature. But the dependency of voltage and how temperature, for every 1 degree rise in temperature, for forward bias, the voltage decreased by 2 millivolt. The third one is the breakdown region that we read just before, that two type of breakdown occur. One is that avalanche, one is Zener Effect. Okay. Now we are going to model the positive half, that is the forward bias. So that is one is exponential model, that is this is the exponential curve, I equal to Is e power V by Vt. So here what we are taking, this I is much greater than Is, that's why we are neglecting this Is. So I can write my current, which is nothing but approximate to Is e power Vt by Vt. Okay. So there are two methods to examine. One is graphical method, one is iterative method. Graphical method means if we will draw the current, that is nothing but Vd minus Vdd upon this resistor R. Okay, so this current, so how to find the two value, current and voltage? That is I have to do graphical method. I have to make one terminal 0 and then make second terminal 0. I can get 2 points. If I will join this line, I will get a straight line. So that straight line will touch the exponential curve, and that point is called operating point. And second one is the iterative analysis. Iterative means I have to go step by step. I have to apply V and then find I, then again taking the new value of V and I to find the second value of V and I, like that. And third one is the constant voltage drop. That is the voltage drop across a diode is what we are taking. It is a constant value of 0.7. Okay. And for ideal diode, voltage is equal to 0. Then the small C analysis. What is small C analysis? This is the diode which is working. This is the diode which is working when a large input is given. Now, along with the large input, we are going to add a small input. So this is the small input that is given to this diode. So as this curve is non-linear, we are going to take a point, Q point, and across just a section for which this curve looks like a straight line or a linear curve. For that section, we are going to take an input. We are getting an output, and what we are seeing, the output is nothing but an amplification of this input. It means for this section, it is act as a linear amplifier. So this you can see here, the linear amplifier is there. That's how the technique small signal is implemented. So before only here you can see the only VDD was applied, but along here VDD along with small AC signal is applied. So here the current that we are getting, that is because of VDD, is only ID. Here the current will divide into two parts. One is nothing but my ID, that is DC component. One is because of AC component. Okay, and because of AC component we will get a value of resistor, which is nothing but VT upon ID. So this is what is the how to find this resistor. This resistor is nothing but inverse of the slope of this curve. Inverse of slope of this tangent of this curve, we will get the value of RD. Here see the RD equal 1 upon slope of the tangent to the IV curve. Okay. Now we'll see in reverse bias. In reverse, this is the condition for forward bias. We see what is the forward bias, what are the criteria that can be applied, the current and the small signal analysis, and for the resistor. And similarly for the reverse bias, you can see here it is the reverse bias. This is the reverse bias condition, or sorry, this is the for reverse bias. This is the breakdown region, and we are interested to find, interested to know what is happening in breakdown region. This is the saturation value. Here there is a change, so that's why we are interested to find this RZ. Okay, this is called incremental resistance for reverse bias. So that is nothing but del V upon del I. Till this point, till the knee point, this voltage and this current is saturation, and here the current increases rapidly. So as there is a small increase in voltage, my current increases rapidly. So, okay, just one thing. Here, this is the VZ, this is the knee voltage. Okay, this is nothing but the voltage at test point. At test point I am taking, which is having a current IZT. At that point, this is the voltage VZ. And here is a term VZ naught. This VZ naught and VZK, this knee voltage and this voltage are almost same. In video, I told you that this voltage same, but that's wrong. This voltage and this voltage, they are approximately same. So, this is the symbol for a Zener diode. And this Zener diode VZ across VZ can be represented like this. This is the VZ, which is nothing but VZ naught into some current into resistor. These two are not same. Remember, these two are not same, but these two VZK and VZ naught, these two are same. Okay, so I can write my VZ, which is nothing but VZ naught, and IZRZ. So I can replace a Zener diode with a voltage source of VZ naught with a RZ value. What is the value of RZ? Which is nothing but del V upon del I. Okay. So now what is the effect of temperature? We have already seen that for the Zener diode, it is a negative temperature coefficient, and for avalanche effect, that is the positive temperature coefficient. So based upon the two, this is the derivation. Now rectifier circuit. What is the rectifier circuit? There are two types of circuit. One is half wave rectifier, one is full wave rectifier. So the diode rectifier will give me output like this or like this. But this is not AC. So what we are going to add a filter, then voltage regulator will get a value AC. Okay. So for half wave rectifier, this is a not ideal case. Means for diode, across the diode, it is a voltage of 0.7. That's why the output and input are not exactly same. Here see, this is the blue one is the input, the red one is the output. The output is coming after certain voltage, that is 0.7 volt. Okay, here you see the IB output or the input current voltage relationship. After some voltage, then the output is coming. Now this is the full wave rectifier, means for both positive and negative half this is coming. For one half this diode is conducting, for second half this diode is conducting. So this is the output versus input. For positive half this is the output, and for negative half after VT value this output is conducting. There are two types. This is the center tap, and one is there, that is the bridge rectifier. What is bridge rectifier? This is the bridge rectifier. It looks like a Wheatstone bridge, and for the positive half this diode and this diode is conducting, and the current flowing through this resistor and the output we are getting. And for this reverse bias, these two diodes are conducting. So this is the output for reverse bias. Here you see the output voltage is bit less than this center tap, because in center tap what is our output, which is nothing but maximum value of Vs minus 1 voltage drop. But here since two diodes are conducting at the same time, the output will be reduced by 2 Vt. But here one advantage is that peak inverse voltage, that is nothing but the reverse voltage across the diode. Okay. So this is the reverse voltage across the diode. We will find the reverse voltage. We will find our peak inverse voltage, nothing but Vs minus Vd. And for bridge for center tap, that was nothing but Vs minus 2 Vd. So here the bridge rectifier having a less peak inverse voltage. Now what we will do? We will add a capacitor. If you see the first diagram over here, this is the application. After diode rectifier we are using a filter. So this is the case that we are using a filter. So filter means including a capacitor. So the capacitor will make my output looks like a straight line. You can see for this half this capacitor is charging, and for the all other half, since there is no other component, the charge is fixed. It is the fixed charge. This is the for ideal case. Now we are taking a capacitor with a resistor, so a load, so that you see for this half, for positive half, the capacitor is charging, and when this voltage is less than this side voltage is less than this voltage, it is disconnected, then the capacitor will discharge through the resistor. So this is the path when the capacitor is charging, and for the rest path it is discharging, charging, it is discharging. So it looks more close to my DC signal. So what will be the total current, which is nothing but IC and IL. The summation of two current will give me the diode current. You see, if this is the output, What will be my IL? That is the load current, which is nothing but same as output diagram divided by R. If this is my output, V output, what will be IL? IL is nothing but V output upon R. Means this value by 10. Let's take this R value 10. This value by 10. This value 10. So what will happen? It will become the same, just decrease in amplitude. So this is the diagram, which is nothing but the same format with decrease in amplitude. And for this path only, for this path, this ID is connecting, this time interval delta t, ID is connecting, means diode is conducting. That's why only for this T1 and T2 interval my diode is conducting. That's why the current is high value, then the current is decreasing. Okay. So now there is a term that is called precision half wave rectifier. What is precision rectifier? Actually for a half wave rectifier we have to supply a voltage that should be 0.7 volt, then only the diode will work. But here for a precision rectifier it can work a voltage of 100 millivolt, 10 millivolt, 1000 millivolt, very less value. For less value also this op-amp, we are going to add a op-amp. It is not positive, it is negative. This op-amp will amplify the small input to a high input, so that will be sufficient for the diode to conduct. So a precision rectifier can be worked at very less input. So that is called a super diode. Okay, this is a rectifier circuit, but it is using a op-amp with a diode. It gives me a super diode. Now there are some special diode that we have just discussed in the last videos. That is Schottky barrier diode, and next one is the varactor. That is by applying voltage, the CJ change, that is called voltage variable capacitor. Then the photodiode means we are apply light and we will get our current. And what will in LED? In LED we will apply current, we will get our light. And then the 7-segment display, we can represent any number by using these pins. And then the LCD, liquid crystal distal, that how a pixel that is formed in our skin, that is how it is on, off, and how it is on. Okay, so these are the processes, and I have written this. So this is the end of this video. This is the first module is completed. Now from the next class we will start our third module, that is nothing but logic gate and binary number system.